Hello students. Welcome to part 4 of the lecture series on filter design. We have already covered 3 parts of the lecture series and we have discussed 2 methods to convert analog filter into digital filter. So we are on now up to the now we will start method 3 for filter design for filter design, that is from analog to digital filter, and this method is called bilinear transformation method. Okay, now as we have seen that the method 1, that was backward difference method, and we have seen the method 2, that is impulse invariance transformation. Now in method 1 we have clarified that it is not suitable for high pass filters and the band reject filters. In impulse invariance transformation, the transformation of the left half plane was into the unit circle in the z plane. So left half of the s plane into the unit circle in the z plane. But there was a problem that if you see the transformation from continuous frequency omega to discrete frequency sigma, then it is many to one transformation, and that's why impulse invariance transformation method is also not suitable for the higher frequencies. That is, it is also not suitable for the high pass filters and the band reject filters. So these two methods are not suitable for the high pass filters and the band reject filters. So we designed a new method that is called bilinear transformation method, BTM, where there is one-to-one mapping between S and Z plane. So there is no problem of many to one mapping. Okay, there is one-to-one mapping here. So let's see how it is designed. Okay, so let's start with the system, that is analog system HAS, that is equals to B upon S plus A. So we can say that YS is equals to B upon S plus A into XS. YS into S plus A is equals to B times of XS, and A times of YS plus S times of YS is equal to B times of XS. So in the time domain, this can be written as dyt over dt plus A times yt is equal to B times xt. So now if we integrate this equation over the time axis on the limits t equals to n minus 1 capital T to nt, then we can see that the equation will become dyt over dt multiplied by dt integrating from n minus 1 capital T to nt plus A times of n minus 1 capital T to nt yt dt is equal to B times integration n minus 1 capital T to nt xt. Okay, dt. So now we will use a rule that is called trapezoidal rule of integration, which says that integrating n minus 1 capital T to nt at dt is equal to capital T by 2 value of a at nt minus plus value of a at n minus 1 capital T. So using this trapezoidal rule of integration on the above equation, we can see that. So we'll get from this above equation y of nt minus y of n minus 1 capital T plus a capital T by 2 y of nt plus y of n minus 1 capital T, okay, is equal to bt by 2 x of nt plus x of n minus 1 capital T. Okay, now if I remove capital T from here, because capital T is a constant, so the above equation can be written as yn minus 1 plus at by 2 yn plus yn minus 1 is equal to bt by 2 xn plus xn minus 1. Now taking the z transform of this equation, we can see that yz 1 minus z inverse at by 2 yz 1 plus z inverse is equal to bt by 2 xz 1 plus z inverse. Now from the above equation, we can see that hz, that is equals to yz upon xz, will be equal to b upon 2 upon capital T 1 minus z inverse upon 1 plus z inverse plus a. Now if we compare the equation, let us say this is equation number 2 and the system which we had written in the starting, that is this is the system number 1. So this is equation number 1 and the equation number 2. Now this is the analog system in equation number 1, and in equation number 2 we have the digital filter. Okay, so now comparing the digital filter and the analog filter in equation number 2 and equation number 1, we can say that S is equal to 2 by capital T 1 minus Z inverse upon 1 plus Z inverse. Okay, so this is the important result for bilinear transformation, the relationship between S and Z. So they can ask you the relationship in 1 marker question directly also. Okay, now this can be rearranged and S is equal to 2 upon capital T Z minus 1 upon Z plus 1. So this is also a relationship. Okay, and you can rearrange this equation and you will get that Z is equal to 1 plus capital T by 2 S divided by 1 minus capital T by 2 S. Okay, so these three relationships, you must just have a look at these relationships, because they can ask you these questions like in 1 marker question, like what is the relationship between S and Z. Okay, so I have to add a page here. Okay, now so So now let's move on. And okay, now this is the relationship between S and Z. Okay, now as we know that Z is equals to R e to power j, the digital frequency. So so now putting this, we get that S is equal to 2 by capital T, using this equation, R e to power j, the digital frequency, minus 1 upon R e to power j, digital frequency, plus 1. Okay, now multiplying the numerator with R e to power j sigma plus 1, multiplying in the numerator R e to power minus j sigma plus 1 upon R e to power minus j sigma plus 1. Okay, now solving this, we will get 2 upon capital T. Okay, now we will solve this and we'll get R square uh, plus R e to power j sigma minus R e to power minus j sigma minus 1 divided by R square plus R e to power j sigma plus R e to power minus j sigma plus 1. Okay, now we will solve this. We will get 2 upon capital T. So this will give us a cos term, and this will give us a sine term. So this will give R square plus 1 divided by R square plus 2R cos sigma plus 1 plus j 2R sine sigma divided by R square plus 2R cos sigma plus 1. Okay, so this is the, so I can say that this is equal to S. Now S is equals to sigma plus j omega. So the real part of S, that is equals to sigma, is equal to the real part of the right hand side. So real part of the right hand side. So this, the real part sigma will be equal to 2 upon capital T R square plus 1 upon, okay, and the complex frequency, sorry, the continuous frequency omega will be equal to 2R sine sigma divided by R square plus 2R cos of sigma plus 1. Okay, so these two equations are there. This is equation number 1 and this is equation number 2. Okay, so this is the important relationship. I don't think no one will ask you this lengthy, this is R square minus 1, sorry, R square minus 1 here also. So no one will ask you this expression written in equation number 1 and equation number 2. I'm just telling you for the sake of completion of the bilinear transformation. Okay, now I will add one more page. Okay, now we can see that equation number 1, we can see that whenever R is less than 1, then the real part of s will be less than 0. And when r is greater than 1, then the real part of s will be greater than 0. So we can say that in z plane, the region inside unit circle is similar to the left half of the s plane. Okay, simple. We can see this now from equation number 1. Now equation number 2. So from here we can see that if we have stable analog filter, then it will transform into stable digital filter. Okay, now from equation number 2, if you look at equation number 2, then equation number 2 is this: omega is equals to 2r sine on r square plus 2r cos. Okay, now let us say that we are talking at the imaginary axis, and since the imaginary axis corresponds to the unit circle, or a circle with unit radius, so imaginary axis corresponds to r equal to 1. So imaginary axis in s plane corresponds to r equal to 1, the unit circle in the z plane. So applying the condition of imaginary axis on the equation number 2, we can say that at imaginary axis omega will be equal to 2 sine sigma upon 1 plus 2 cos sigma plus 1. Okay, so the denominator here will be 1 plus 2 cos sigma plus 1. So this will come out to be 2 sine sigma upon 2 plus 2 cos sigma, that is sine sigma upon 1 plus cos sigma, is the imaginary axis, is the omega. Okay, now this can be easily transformed into omega equals to 2 sine omega by 2 cos omega by 2 divided by 2 cos square omega by 2. So sorry, sigma. Okay, now this can be solved and we will get that this is equals to, I left 2 by capital T. Yeah, so there is a modification, 2 by capital T is also there. Okay, I just left that. So this will come out to be 2 by capital T tan of omega by 2. So this is the relationship that you should learn. So the continuous frequency omega is equals to 2 by capital T tan of digital frequency divided by 2, or the digital frequency is equal to 2 times tan inverse omega t by 2. So these two relationships are very important, and remember that this is the relationship only at the imaginary axis. On the other axis, for other uh, axis, there will be a different relationship. Okay, so this is very important. Only this you have to learn. So this you have to learn. Okay, now as we know that omega varies from minus infinity to infinity. Now if I put omega minus infinity to infinity values, then this tan inverse will only give me the values from pi to minus pi. Now this is the plot between the digital frequency and the continuous frequency. So the continuous frequency sorry, is varying from minus infinity to infinity, and we can see that the tan inverse function will vary from minus pi to pi. Okay, and we can see that this is one-to-one relationship. One-to-one relationship. Okay, so the problem which we were facing in the impulse invariance transformation, that there was a many to one mapping. Okay, that is removed here, but there is a one more problem which we will face. So that problem is called, okay, so this is clear. So one more problem which we will face is the problem of frequency warping. Okay, what is this? Now, since the relationship between the digital frequency and the continuous frequency is non-linear function, so this is why frequency warping is happening. So now let's look at the meaning of frequency warping. So for this, let me copy the figure and paste it here. Okay, now just look at the continuous frequency omega axis. So let us take these values. So I'm marking the values with green. So these values will be these values on the digital frequency axis will be visible over this region. Now for these frequencies, if the width of red and green is same, but you can see that the width of red will be reduced on the digital frequency axis. Similarly, the third one, if I take, then the width will be further reduced on the digital frequency axis. Now what we can see here is that due to the nonlinear relationship, sorry, the relationship was omega t by 2. Okay, so now due to this nonlinear relationship, what is happening is the lower frequencies of the continuous domain, that is omega domain, are expanded on the digital frequency axis, but the higher frequencies of the continuous domain are compressed on the digital frequency axis. So this is what the frequency warping is. Now they can ask you this what is frequency warping in the bilinear transformation. So this is the simple thing, and you can easily visualize this also. The lower frequencies are approximately of the same width on the digital frequency axis, but the red one is reduced and the purple one set is further reduced on the digital frequency axis. So the higher frequencies are compressed on the digital frequency axis. So this is what the frequency warping is. Now let's look at the effect of frequency warping, that what will happen by the frequency warping. So this is the, so let us say that HA omega is the function of the continuous time filter or the continuous time system, and mod of HA omega shows the magnitude and angle of HA omega shows the phase. Okay, and here we can see that, so I've drawn the figure here. So here we can see that it's a linear phase system. Okay, so we are talking about the continuous time system. Okay, and here the magnitude plot is like this. So it is non-zero over these frequencies, non-zero over these frequencies, and non-zero over these frequencies, and it's a linear phase curve as we can see here. Now the transformation from the continuous frequency to the discrete frequency is drawn here. It's a nonlinear curve. So the magnitude response in the discrete domain will change. Okay, so we'll be mapping here. So what is the mapping taking place? So these frequency mappings are taking place here. Okay, now if we say that the width of these frequencies on the continuous frequency axis is same, let us say this, but the width on the discrete frequency axis will keep decreasing as the value of continuous frequency omega increases. Okay, so we can see that, so the width decreases. Now this is because of the frequency warping. Okay, very simple to understand. Now same is the effect on the linear phase. So if this is a linear phase, then by mapping we will get the phase of the discrete system as a non-linear. Okay, so this is the effect of frequency warping that will take place. Now let's look at one or two examples. So it is given that, so this is question number 1. So the example is HAS s plus 0.1 divided by s plus 0.1 whole square plus 9. So this is the analog filter. We have to convert this into a digital filter with omega r is equal to pi by 2. Okay, so we can see that analog so a digital filter with sigma r is equal to pi by 2. Now in the analog filter, omega r is equals to 3. Okay, so you can see that. So since we have the relationship that omega is equal to 2 by capital T 10 of okay. So we can get the relationship that 3 is equal to 2 by capital T tan of pi by 4. So T is equal to 2 by 3. So we get capital T value. Now, as we know that Hz is equals to HAS, where S is equals to 2 upon capital T 1 minus Z inverse upon 1 plus Z inverse. So easily we can replace S by this function in the equation. So S plus 0.1 upon S plus 0.1 whole square plus 9. 2 by capital T. Now we know 2 by capital T is 2 by 3 Z inverse upon 1 plus Z inverse. So this will come out to be S equals to 3 1 minus Z inverse upon 1 plus Z inverse. Okay. So putting the value of this S, we will get that it is Hz is 3.1 plus 0.2 Z inverse 2.9 Z to power minus 2 divided by 18.61 plus 0.02 Z inverse plus 17.41 Z to power minus 2. So such type of questions can be asked. So similar examples are given. So there's one more example. Let me solve this. Example number 2. So here HAS is given to us, that is 4 upon S plus 3 into S plus 4. Capital T is given to us 0.5. We have to find Hz. So very simple question. So here Hz will be equal to 4 upon S plus 3 S plus 4, and S will be equals to 2 upon 0.5 1 minus Z inverse upon 1 plus Z inverse. Okay, now simply we will put S is equal to 4 1 minus Z inverse upon 1 plus Z inverse, and after solving this we will get Hz will come out to be 1 upon 2 1 minus1 plus Z inverse whole square divided by 7 minus Z inverse. So these kind of questions can be asked. So this is sufficient for the IIR filter design. In the next part of the lecture, we will be completing the FIR filter design. So that's a very small topic. Okay. So thank you guys. Keep sharing the lectures and keep giving us the feedback. So thank you.